Now we have results from a survey. And first we want to know the probability that a randomly selected viewer will rate the new show as average or better. One thing we'll need to know here is the total frequencies. And if you add these up, they add up to 80. So average or better would be average, above average, or excellent. So we're going to add up all those frequencies and divide by 80 to get our probability. That adds up to 61. If we divide this, we get 0.7625. That would be our probability. Now we're going to pick numerical values for each of the ratings. So from poor at 1 to excellent at 5, and write down a probability distribution. For each one of these, we're just doing the relative frequency from our table. So we're taking each frequency and dividing it by 80, since that was our total, and that gives us our probability to go into our distribution. And again, when we get this all done, if we want to check that we've done our arithmetic right, we can add up all of those probabilities and they should add up to 1, or they should be very close to it. Again, we might have a little bit of rounding error, but there shouldn't be very much. So there is our probability distribution. Now we're going to do a little bit more with the same problem, so I'm writing down our probability distribution that we just found again. Now what we're going to do with this, once I get all these written in, is to find the expected value. And remember, in order to do that, you add a third column to your table, where you multiply each x value times the p of x value, and then you just add up that column, and that total is your mean. For our first row, we're multiplying 1 times the 0.075, which is 0.075. For the second row, we're multiplying 2, which is the x, times the 0.1625. For the third column, we're multiplying the 3 times the 0.2125. And remember now, we're not doing probabilities anymore, so some of these numbers can come out to be negative, some of them can come out to be more than 1. But when we do have all those, then we're going to add them all up. And if we add all these values together, we get 3.5. That means our expected value is 3.5. Notice we don't have to divide it by anything for this. Okay, now if we consider the experiment of selecting 20 viewers of the show at random and recording their ratings of the show, would this qualify as a binomial experiment? Since we had 5 different ratings, that means we have more than 2 possible outcomes. And that means that it's not a binomial experiment. To be binomial, there can only be 2 possible outcomes. To get our probability. Now here we had a survey in New York that found out of a total of 131,831 rent-controlled housing units, 32,958 were built after 1946. Suppose that 20 units are selected at random with replacement. The first question is, what's the probability that exactly 3 units out of the 20 were built after 1946? Well, here, if you notice what we have, there are only 2 possibilities. It either was or it wasn't built after 1946. So here we do have what we consider a binomial probability. And the numbers are big enough that we don't have to worry about sampling with or without replacement, actually. So if we consider this as a binomial experiment, we've got our 2 outcomes. We've got 20 trials, which are the 20 units that were selected at random. And our probability of success would be the 32,958 divided by the 131,831, which just happens in this problem to come out to be 0.25. So we have a binomial experiment with 20 trials, a value for p of 0.25. And now we're trying to find the probability that x is exactly 3. So I put a binomial probabilities table in here just like you'll have on your test. So we look in the p equals 0.25 column and look at where x is equal to 3, and we just pick out that value. So our value is going to be 0.1339. Now, to use your calculator for this, you'd use the binomial PDF, since we're only talking about one value, exactly 3. And for the TI calculator, you put in the n, and then the p, and then the x. So you'd put in 20 and 0.25 and 3. And it should give you something very close to what was in the table. Now, for the probability that at least 10 were built after 1946, at least 10 means we're including the 10, and we're going from there all the way up to 20. If we're going to use the table, we're going to have to find the probabilities for each one of those values and add them all together. So here, if we're starting at the 10 in the 0.25 column, and we're going to go all the way down, and notice that most of those values in this table are 0. So we only actually have 4 that aren't 0 that we'll have to add together. What we're actually doing again here is the probability that x is greater than or equal to 10. And there's the probability for exactly 10, for exactly 11, for exactly 12, and exactly 13. And then after that, they were all zeros for the probabilities. So that's going all the way up to 20. If we add all those together, we come out with 0.0139. Now, to use your calculator, there are a couple of different ways you could do this, but the easiest one would be to use the binomial CDF function so that you don't have to add too many values together. Now, since we're looking at the probability from 10 going up, your calculator function goes from 0 up to whatever number you put in. So we'll have to use the complement in this problem, and that means we have to subtract from 1. So the complement of the set from 10 up to 20 would be from 0 up to 9. So we're actually going to find the probability that x is less than or equal to 9, and then subtract that from 1 to get our final answer. And it's important to find the less than or equal to because that's what your calculator function uses. So we're going to use binomial CDF with 20 and 0.25 and 9 for our x value, and then subtract that from 1. Now, the probability that less than 3 units were built after 1946, less than 3 means we're not including 3. So this would only be 0, 1, and 2. Again, going to our table, we look up the 0, the x equals 1, and the x equals 2, take those 3 values and add them together. So our probability that x is less than or equal to 2, we're taking the x equals 0 probability, the x equals 1 probability, and the x equals 2 probability, and adding them, which gives us 0.0912. On your calculator, again, you have to do the less than or equal to, so you'd use the binomial CDF function with 20, 0.25, and 2. Now suppose that we change this a little bit and we decide to select 300 units. And if x is going to be a random variable representing the number of units out of the 300 that were built after 1946, all we're going to do here is find the mean and the standard deviation for x. And these are this is the one place I will ask you to find a standard deviation because the formula is so easy. So for the mean, again, we've got our n is 300 and our p is 0.25. So the mean for this is just n times p. We just take the 300 times the 0.25, and that's going to give us 75. The standard deviation is the square root of n times p times q. And remember that q is just 1 minus p. So we'd have 300 times 0.25, and 1 minus p would be 0.75. If we multiply those under the square root, we get 56.25, and then our square root would be 7.5, so that would be our standard deviation. Now here's some problems from chapter 6, and in these three we're assuming that z is a standard normal random variable. In other words, we have a standard normal distribution. That means our mean is 0 and our standard deviation is 1. So the first problem is just to find the probability that z is less than negative 1.64. We'll do this both with the table and with the calculator function. So again, I really do recommend that you draw these pictures. Here's our standard normal distribution with 0 in the middle for the mean. We have our negative 1.64. Our inequality is going to the left, so we shade to the left. To use our calculator, we'll have to use a lower bound there. We can use negative 10. So we do normal CDF with our lower bound of negative 10, our negative 1.64, and then tell it the mean and the standard deviation. Now if we use the table, since the shading goes to the left, all we have to do is look up our z-score, which is negative 1.64. And here's half of the table. And if we find the negative 1.6 is in that row and the 0.04 is that column, where they intersect is right there. So there's our value of 0.0505. That means our probability that z is less than negative 1.64 is approximately 0.0505. That should be close to what you get on your calculator. Next problem is the probability that z is between 1.03 and 2.75. Again, we're drawing the picture. We're drawing in both of those values, the 1.03 and the 2.75. And we're going to shade in between those two. If you're using your calculator, this is pretty simple. You just put in those two values and then the 0 and the 1 for your mean and standard deviation. So it would look like this. For the table, we're going to have to look up each different value in the table and then subtract the two probabilities. So we're going to look up the 1.03, look up the 2.75, find the probabilities for each, and then subtract. So here's our positive z-scores table. We have the 1.0, and there's the 0.03 column. So where they intersect is right there, 0.8485. And then for the 2.75, we got the 2.7 and the 0.05 column. And where they intersect is right there. So our probabilities are 0.8485 and 0.9970. If we subtract those two, we get 0.1485. Now finally, we're going to find the value of z that separates the bottom 17% of the z-scores from the top 83%. And remember, no matter whether you're using the table or your calculator, for problems like this, you always have to look at the bottom part. If it only gives you the top, then figure out what the bottom would be. That would be the complement of it. So here's a picture of our bottom 17%. And remember, the 17% is actually the area in there. We're going to convert it to a decimal form, so it's 0.1700. That's our area, and we're trying to find the z-score that goes with it. On your calculator, you're going to use the inverse norm function. All you have to do is put in that probability or the area for the left part of the graph and 0 and 1. In the table, we're going to find the value in the middle of the table that's the closest to 0.1700. And I always write those with 4 decimal places because that's how the values in the table look. So if we look through the middle of the table, we can find these two values that are both on either side of 0.1700. I'm going to write both of those down. We have 0.1711 or 0.1685, and actually 0.1711 is a little bit closer to 0.1700. That's the one that we're going to use. Now we just figure out what row and column that came from. So it was the negative 0.9 row and the 0.05 column. That gives us a z value of negative 0.95. And we can put it in our picture over here. Now, one last slide here. This one we've got a normal distribution, but it's not a standard normal. We've got a different mean of $18 and a standard deviation of $8.05. So our first problem is, what's the probability that a company will have a stock price of at least $30? We're drawing the pictures again. Our mean of $18 goes in the middle. And at least 30 means that we're going from 30 to the right. So we're going to shade to the right. To write it in probability notation, we're finding the probability that x is greater than 30. For your calculator, you can use the normal CDF. You have to put in an upper bound. Just make it something nice and big so it's way far away from the mean. I used 1,000 for this one. And then put in your mean and your standard deviation. For the table, since the shading goes to the right, we're going to have to use the complement, because remember, in the table that tells you what would happen if the shading went to the left. So we will look up the z-score for the 30 and then subtract the probability that we get from 1. Finding our z-score, again, this is just x, which is the 30, minus the mean divided by the standard deviation. That gives us 1.49. And if we look that value up in our table, there's the 1.4 row and the 0.09 column. So there's our value of 0.9319. So again, what the table gives us is the less than. So the probability that z is less than 1.49 is 0.9319. If we subtract that from 1 to get our answer, we get 0.0681. That should be close to what you got on your calculator if you did it with your calculator. Now, next question. Oops. So our two areas, the one that we found from the table, the 0.9319, was going to the left of the 30, and the complement is going to the right of the 30. Next question is, what's the probability that a company's stock price will be between $15 and $25? So we have our picture again with the 18 in the middle, and we'll mark the $15 and the $25. We're going to shade in between those two. If you want to use your calculator for this, all you have to do is put in the 15 and the 25 for your two values, and then put in your mean of 18 and your standard deviation of 805. So there's the calculator function. Now, to use the table, since we're between two values, we'll have to find z-scores for both the 15 and the 25. We'll have to look up each z-score in the table, and then we have to subtract the probabilities. So for our z-score for 15, we're going to take 15 minus 18, divide by 8.05. And since this value was on the left side of the mean, we're going to get a negative z-score. We get negative 0.37. For our z-score for 25, we take 25 minus 18, divide by 8.05, and that one, since the value was to the right of our mean, we get a positive value, positive 0.87. Now what we need to do is look both of these values up in our z-scores table and get our probabilities. So here we're looking up the negative 0.37, so we have negative 0.3, 0.07 for the column, and we get a value of 0.3557. For the 0.87, we have to go to the positive z-scores table, so we look up the 0.8, the 0.07, and we get 0.8078. So now we have both of our z-scores, and then to get our final probability we're going to subtract. So we take the 0.8078 minus the 0.3557, and our final answer is 0.4521 for our probability. Now next we're going to look at the minimum stock price that a company would have to have in order to be in the top 15%. So I'm drawing the distribution again, and top 15% means that we're going from some stock price to the right to get the top 15%. Now again, since this isn't what our inverse normal function on our calculator or our z-scores table gives us, since it gives us values going to the left, we're going to have to think about what the complement of that particular area would be. So we have the 15% there. If we write it in decimal form, it's 0.15. So our complement would just be 1 minus that. That would be 0.85. And again, I'm writing it with 4 decimal places to make it easier to look up in the table. For your calculator function, you'd put in inverse norm, the 0.85, and then your mean and your standard deviation. To look it up in the table, we're going to find the closest value in the middle of the table to 0.8500. So if we look through the table here, the two values that are the closest are 0.8485 and 0.8508. So we want to choose between one of those two, and we just want to choose the one that is the closest to 0.8500, which would be the 0.8508. Now going back to the table, the z-score that corresponded to that would be 1.04. That gives us our z value, but we still need to go back and find the x value, which would be the cutoff stock price. So again, if you're using the table for this, you can use that little formula I gave you, which is you take z times the standard deviation plus the mean, and if you do this, you end up with a stock price of $26.37. Next problem. In this one we have a random sample of 25 stocks, and we want to know the probability that the mean stock price for the sample is less than $16. The key words in this are that we have a sample of 25 stocks. We aren't just selecting one stock at random, and we're trying to find a probability that has to do with the mean stock price. So we're looking for a probability that has to do with a sample mean. That means that we have to think about those sampling distributions and think about what the mean and standard deviation are for sampling distribution for sample means. And if you remember, the mean is going to be the same as what we already had, so the mean will be 18. What's different is going to be the standard deviation. And remember, for the standard deviation for a sample mean, we take our original standard deviation, which was the 8.05, and we have to divide that by the square root of the sample size. We're dividing it by the square root of 25, and that's going to give us 1.61 approximately for our new standard deviation. We're still looking at a normal distribution. We still have the same mean as we did before, but when we do our calculations, we're going to use that new standard deviation instead of the 8.05. So here's our picture. We're putting the 16 in there and shading to the left since we're doing a less than. If you're using the calculator, then you need to find a lower bound, and I just used negative 100 in this one. If you're putting it into your calculator, you have the normal CDF with negative 100, 16, 18 for your mean, and 1.61 for your standard deviation. to look it up in the table, since it's a less than problem already, we just have to look up the z-score. We need to find the z-score for 16. So we're taking 16 minus 18, and remember to divide by your new standard deviation. 16 minus 18 divided by 1.61 gives us a negative 1.24. Now to look this up in our z-scores table, we just have to look up that value, and since it's a less than, that will give us the probability that we're looking for. So here's our negative z-scores table. So we're looking for negative 1.2 for our row and 0.04 for our column. And that takes us down here to 0.1075 for our probability. So our probability that the mean stock price for the sample of 25 stocks is less than $16 would be 0.1075, or only about 11%.